Cool, we're recording. So the topics for today are some follow-up from last time on how Gitaly integrates with GitLab CE, and then after that we want to look at how Git push and Git pull via SSH works. And hi, I'm Jacob. Maybe you can see in the recording already, like I'm staff backend engineer on the Gitaly team, and with me are Paul and Francisco and John, who all are also backend engineers at GitLab, and so that's the audience, or that's who's in the call. So what did I want to say about? Okay, I just did the recap. I guess I should do the recap again. Last time we looked at GitLab CE and how all Gitaly calls sort of start in Gitaly clients in this file. They all go through the call methods. So that would be self.call. And this is the one point that all gRPC calls go through in GitLab CE. And so this is sort of where we left off. An important other commonality to almost all gRPC calls is that almost all calls involve a repository. So what is a repository? And repositories are a bit weird, so I just wanted to go into that. So let me look for gitaly-proto. I don't have a window open, so let me make a window. And I guess that would be in shared.proto. Yeah. Yes, repository. So what is a repository? It is primarily this, a storage name and a relative path. Then there's some other stuff that we should just touch on. This is one area, and then there's this. And we can forget about reserved stuff. So what do we have here? Storage name. This is a string field, and the typical example would be the string default. So these are the same names that are in GitLab's config file, where we have a mapping between storage names and Gitaly addresses. These names are in the database. Every project record in the SQL database on the GitLab CE site has an associated repository storage field. So that's what would go into this field, into the storage name. And in the Gitaly config, we define which storages this Gitaly server is serving. So yeah, that's this field. And then there's the second field, relative path, which sounds a bit funny, but we used to have a full path there with an absolute path, which was, in retrospect, makes no sense. So what relative path really means is, so in your Gitaly config, let me pull up a Gitaly config file. Here's the example Gitaly config file. You will have something like this. So this is the definition of a storage. Say the default storage, say the storage name default would be served by this Gitaly server and would be at this path. Then every request that comes in says, well, I want to, every request needs to reference one of these things. So it would say, okay, I want to have a repository that's on the default storage. And then this would be something like, so this would be a path name ending in .git usually. And then the actual repository on the Gitaly server is then found by putting these two things together. So you would end up in home git repository / gitlab.org / gitlab-ce.git. This was sort of our starting point. Well, this is still how it works. The one thing I wanted to touch on is the funny fact that here we have a name which is human readable. This is the old situation, and we're changing to a new situation called hash storage. This idea of passing this name here is very problematic because this name can be changed by the user. A user can just come in and rename their repository. And when that happens, we actually have to make a gitaly call and rename the directory on disk. And this sort of thing can go wrong. So it can happen that a user updated, that in SQL, the project name was updated to another path, and then the rename on the Gitaly server failed, and then your repository can no longer be found. It's just gone. So that is very messy and problem. It leads to weird bugs, and there's just having to keep those two things in sync is annoying. So we are in the process of moving to something called hash storage, where the idea is that we have an immutable name for the repository, and it's just derived from the SQL ID, and it goes through a hash function like SHA-256 or something. That's why it's called, I guess that's why it's called hash storage. So on a production server on gitlab.com, you will probably see a mix of things that look like this, or they will look something like, and I don't know by heart, but okay, that is not hex. Imagine me typing some hex code here. Okay, let me just now be a nerd and so now we have some hex. That's too much. Let's delete that. So it might look something like this. And these two things are mixed. And this is, when you're working on Gitaly, it is good to be aware that we're in a transitional stage where you can encounter both these things. And for the most part, Gitaly is completely oblivious what these things look like. It doesn't even care if they end in .git. It just assumes it is a directory, and that directory contains a Git repository. But these are the sort of values that are actually out there in the wild. Any questions about this? Cool.
I have one question, Jacob, about, because the hash name is similar to how Git hash all the reference. So would that structure enhance, for example, lookup for directories or lookup for I don't know, files instead of
the reason it looks like this is that file system limitations. The way, so if you have a lot of repositories and they're all under this thing, if you're unlucky, you're on X2, then there's a limit at, I don't know, 30,000 or 60,000 entries. And if you have more than that, then you get a hard error and you cannot create new repositories. So you want to have some sort of nesting to avoid having very wide directory trees. So because of that, I think maybe we even have 2 slashes in here. So we create a hash, and then we create some prefixes like that. And Git uses the same trick. Git only goes 1 level deep. So if you look in the Git objects directory, let's see if this works. Objects. You see directories like this. And this is the same idea of fanning, of distributing the objects over separate physical directories on disk, because you don't want to have directories that are too wide. And this is also why we use a hash function, because if you just use the project ID, then you get a sequence that is ascending in a very annoying way. Then you don't get a nice distribution. And by I guess one of the properties that the hash function is supposed to have, that you get a more or less uniform distribution over different hash values. So you get nice buckets. I think this was the idea behind it.
Okay, thanks.
Cool. Okay, so that's this one last thing I wanted to tell you about in the context of GitLab CE and Gitaly. So if we have no further questions on this, then we can go and look at how Git Clone works. Okay, so let me close this. Git Clone, and I was going to use SSH, so let me check that I have that set up. Somewhere in here. Zoom puts this weird bar at the top, and then I can't see my tabs anymore. Let's sign in. Come on. Development mode. Yeah, it's doing something. Where's my user? No, that is not my user. Settings.
Development mode will probably be a good talk for next time.
Sorry?
Development mode will probably be a good talk for next time.
Okay, yeah, cool. Yeah, I guess you get to see some of it in passing. So here I went to SSH keys and I already have a key on here, so this should work. So let's see if I can clone a repo from this. So this is just my local GDK, right? Let's go to GitLab tests. It's a small repo. And to copy the clone URL, I'll go into /tmp and do a git clone of this thing. And what happens? Connection refused. I know why that is. That is because there is no SSHD on port 2222. And this is one of the GDK defaults. This is one of the reasons why I wanted you to see this fail, so you know about it. What you need to do then is stop GDK, or actually here I was running the GDK run app, and edit the proc file. Look for SSH. And here there's a commented out line that starts SSHD. So let's uncomment that and boot GDK again. Now this is going to be very slow, but I think I can already make a connection. Yes, internal API unreachable. So where does that come from? Who or what is saying internal API unreachable? This is where we run into GitLab-shell. GitLab-shell is an adapter between SSHD and the rest of GitLab. So what's happening here when I make this connection? Okay, maybe I need to back up a moment and look for the config file. Okay, I can see that here. Let's go here. Let's grab the proc file. So here at the bottom was SSH, and it uses this config file. So let's look at that config file. And okay, so when I make a connection on the server side, it is using this authorized keys file to recognize my SSH key. So this is the basic way to do SSH with keys is that on the server you want to connect to a user account, and then in the user home directory you have an authorized keys file that lists the keys that are allowed to connect. So this is a custom SSHD and it's using this custom authorized keys file. So let's look what's in that file. Do we care about anything else in here? No, so I'm going to throw this file away. So now what is going on here? Let's see. This part is just my public key. Let's take that away for a moment. And this part is an optional thing you can do in an authorized keys file, which is to set extra config options that can apply to any session that connects with this key. The most important config option here is that the command from the client side is ignored and we get a forced command. I think it's literally called forced command if you look in the SSH documentation. So when I make this SSH, this thing makes an SSH connection on this port and tries to run, okay, here's the other side of the story. What this thing actually does is it tries to do SSH port 2222, Jacob Vosmar at localhost 2222. No, wait, doesn't do that. And then it tries to run a remote command, upload git, upload back this. This is what the Git client is trying to do. And this is a remote command it's trying to start. but we're not letting it because we are overriding the remote command on the server side, and it's going to launch this thing instead. And frankly, all these options are just there for security to say you can't do those things, so we can ignore those for a moment. Now, this command is taking us into GitLab-shell. And the other important thing this line is doing is that it's matching this SSH pub key with a logical identifier key 1. And this key 1 corresponds to the SQL database in GitLab. GitLab has a table called keys, and that will have a record with ID 1, and that corresponds to my user and this key. So are you still with me?
So
Yes.
just to recap what I understand, we rely on SSH to actually do the association between a user's public key and the identifier in the database.
Yes, exactly. And yeah, so and this is one of the big jobs that GitLab Shell has in the big picture, is that it needs to make sure that this association happens correctly. Because as far as SSH is connected, there's concerned, there's just one user. And on a production server, that user will be called Git. But we're actually multiplexing that one user into millions of individual users. And that mapping is one of the core jobs of GitLab Shell. So this takes us into this executable, and I think we can just click that executable and it is a binary. where? Okay. It used to be a Ruby executable, but we're trying to convert it to Go gradually, and now there's binary shim, so we can't look at it directly. But what I can talk you through what this does. Let's see, let's go to GitLab Shell. I have it open already, I think, yes. Here's GitLab Shell. We don't care about gitaly-proto right now. Just go to the master branch. So in bin, there is GitLab shell, and I guess, yeah, this one is executable, but this one is a script. So that's the one we want. I happen, or maybe we should, no, I'm going to ignore the, we're going to ignore the executable for now, because it, in the future, all the work will happen in this this Go binary, but I know that right now it doesn't do much. And this is the old executable. So this thing takes that key1 argument, it does some validation on that, and then it goes into a Ruby class called GitLab-shell, which is in the same directory. So let's look at that one. So we live GitLab-shell. And this thing now does a translation between, well, there's a couple things. It's a little hard to read, but yeah, it's not going to help if I'm going to talk you through the code because it's hard to read. So let me try to explain in high level what it does. It makes an API call. Makes API call to internal API. And if that API call says this is okay, then it connects to Gitaly and copies standard in, standard out, standard error, back and forth. And then on the other end, it makes a Gitaly RPC call. So that's that is what GitLab Shell is doing. But like that, it's a very short story. So how do I expand it? Is there what's the first part you want to know about what's going on here?
So yeah, I just wanted to clarify the SSH force command when it's configured like that. Does SSH basically just delegate all of its it just uses that command. It just skips over the kind of SSH client. and its functionality?
Yeah, let's okay. Let me demonstrate what force command does a bit more. So for that, I'm going to mangle my this file here, even though it's managed by GitLab-shell. I'm going to ignore that. Create a new entry, and let's start with just a plain entry where there is nothing. So this is just my key, and now if I would connect to that thing, that's 2222. Then it says operation not permitted. Why is that? Because I haven't saved this file. Now I have a shell session. This would be very bad if this happens on your GitLab server, because then you have shell access as the application user, and yeah, game over. So this is never what you want. So what can you do with force commands? So I can just say command equals echo hello world. And then if I try to connect, it says hello world and end of story. So there's one missing piece here, which you may or may not know, which is that there's two ways of running SSH. If you just run, let me take this out again. If you just run it like this, then you get a shell, and you can do stuff like print working directory. The other way to run SSH is to give it a remote command. If I give another argument to say, run this command for me, then on the other end, on the server, it will just run that command, connect, and like standard input and standard output get connected across the network. Command runs, command exits, session is over. If I run this, I get this. So for security, this is as bad, right? If I can run a single command or whether I get a full shell session, if you get this, you're in. So this is more like what Git is doing, except Git doesn't run pwd. It runs a Git specific, it tries to run a Git specific server-side command that generates a pack file with all the data it's trying to clone. So in this force command, you can do things like, I think it's called SSH original command. And then let's say, hello world. So now if I try to do pwd like this, it will show here that that was the original command that got preserved, but instead it ran the other command, run the second part, echo hello world. But this is the basic principle. A Git client comes in and says specifically, I want to run Git upload back on some repository, and that repository will have a user-friendly name. You look at the clone command I was trying to run. It tries to run something like this. So the Git client thinks that on the GitLab server, there is a directory called gitlab.org/gitlab-test.git, and right there, when you log in with SSH, and that is a repository. That's what the client thinks. That's not true, right? It's not like we have a home directory up there and all the repositories are boom in that home directory. At one point in GitLab's history, it was almost like that, but it was never 100% like that. So there is this translation going on between what Git thinks it's running on the server, and that comes in as this SSH original command. And then it gets translated into, well, we know where the repository actually is, and then we run git upload back in that directory. That's the basic idea, and that's how things used to work before Gitaly. And then with the introduction of Gitaly, it became a little more complex because the server where SSHD picks up the phone is not where the Git repositories are. So instead of saying, okay, I'll just run git upload back in this directory, it needs to establish a Gitaly session and connect to the server where the repository actually is, and then proxy data back and forth to there. Very long answer, but Did I answer your question, John?
Yeah, that makes sense. Yeah.
Cool. So that is the force command mechanism. So it is very important that this file is in order. Something I should say now is that the idea of having this one authorized keys file is something that didn't scale. Like in the early days of GitLab, you would have an authorized keys file, and it would be very long. It would be as long. It would have one line per key known to GitLab. And every time somebody adds a key, we would have to take a lock on that file, update the file, and release the lock. And so first of all, these updates became very slow, but second of all, at one point, that file was 100 megabytes. So every time you would establish an SSH connection, SSHD would have to do a linear search through a file of 100 megabytes, read out pub keys, compare them to your pub key, and see if you're it to find your key. And that linear search just got worse and worse and worse. And in some way, people in the company were oblivious. Some people, I mean, I was not feeling this much because I had a relatively early account. So my key was relatively high in the authorized keys file. So I would have a session much quicker than somebody who signed up a year later. So this whole thing didn't scale. And luckily, around the time this wasn't scaling, the people added a patch to SSHD that allowed you to, instead of having one big authorized keys file, to run a command, to spawn a command where you say, here's the pub key, is this okay or not? So what you find in GitLab-shell, let's see if I can pull that up, and this is one of GitLab-shell's jobs, is that it has an authorized keys command. Okay, looking at this code doesn't tell you much. But what this does is it gets the arguments from SSHD, it makes an API call with just the pub key of the user who's connecting. Then the GitLab Rails application does a lookup in the database in SQL where we have an index on the column that contains these. I think we take a hash of these and then we look it up via that. But at least we have a SQL lookup, not a linear scan of a flat file. We do a SQL lookup to find out the key ID, and then we come back with just this line. So in practice, on gitlab.com, we don't use this authorized keys file anymore. But it's still a valid way to understand what's going on. Cool. So yeah, so this thing has to make an API call. Maybe we should look at that API call a bit. So that would be in GitLab net. No, I clicked the wrong thing. This one.
So if if we're using that script to verify the key, where does the force command come in if we're not using the authorized keys file anymore? Does it get prepended somewhere?
Yeah, it gets prepended. The way that plugin mechanism in SSHD works is instead of taking 100 megabytes authorized key file and scanning through it, you have a command, you feed it the pub key, and then the command either prints out nothing, which means this key was not found, or it prints out a line on standard out that would have been allowed in the authorized key file. So it's almost as if we're generating authorized keys on the fly per request with at most one line in it. But the line looks exactly the same.
Okay, so the API is responsible for prepending that command.
Yeah. Well, strictly speaking, the API returns JSON, and then GitLab-shell renders this this command, because GitLab, this thing has an absolute path in it that depends on the server you're on. So only
got it. Right.
Only the local GitLab-shell knows its path. Yeah. I don't even. Yeah. This. The fact that we need that absolute path is its own interesting problem, but I guess I shouldn't go into that. So yeah, we make an API call. We don't do this one because this one is, well, one of the problems with GitLab-shell is that it does too many things at the same time and they're mingled. Let's see. Well, this is the thing that is an authorized key lookup. But I'm afraid that this function at the top called check access is responsible for setting up the initial SSH connection to the Gitaly backend. And I don't like that because this word changes means nothing in that context. And GL repository is not known, so this shouldn't be outgoing data. This GitLab shell is confusing because of its history. But anyway, what it comes back with is that would be this access status class. This thing will have, let's see, what's this? Gitaly, GL project path, GL repository. This is probably the address. So it's a bit messy, but this thing will build up will roughly build up the arguments. I think that's happening here. So this, repository, GL repository, project path ID, GL username. So what I'm going for is this thing needs to plug into a Gitaly RPC. And I want to find that RPC. Where did I put? I shouldn't have closed gitaly-proto. It's up here. So what are the arguments of an SSH upload back request? It needs a repository. There's standard in data. Standard in data is part of Git's own transport. So if for us it's opaque data that we're just kept copying back and forth. Then there are config options and a Git protocol version. And if we look here, what do we have? We have repository, GL repository, project path, GLID. Okay, GLID is something that is specific to push. We'll look at that later. Okay, that's what I need to get to next. How does this work with push? This is push specific, and this, these two are down here. These two are specific to push, and these three all go. Actually, I'm not sure why this is duplicated because I think GL repository is part of the repository message. So this looks a little confusing. So from this, this goes back into a Go executable because we're sort of stuck in the middle between having, historically this is Ruby, but because the gRPC client in Go is much nicer than in Ruby, when we were doing the Gitaly migration for this GitLab shell stuff, we wrote a gRPC client in Go that does the heavy lifting. So this thing makes this JSON thing, and then it execs into another executable and passes these arguments. And maybe, just maybe we can see that executable if we do first, let's see if we can do a clone, if it even works, because I got completely sidetracked. That would be this command. It says bad line length character git dash. That's because I didn't save my authorized key file. It was still doing this echo SSH original command. And that would be git dash upload dash back. And Git did not expect to get that back. So now this is a clone. And here you can see that SSHD accepted my public key and started the session, and then it was done. So that worked, but what I want to do now is see if I can grab a big repository so that things are slow. And then we can see what's going on better. So if I clone GitLab CE, and if I look up the, let's see, where shall we do this? Let's create a new window. I hope this is SSHD. No. That is SSHD. Okay, so if I go in this window and clone GitLab CE, then that will take a while, and then we can see what happens under SSHD. I'm putting this RMRF here so that I can rerun this command and it'll just work. So I do a bare clone of this thing into slow.git, and now we run ps3 on this end. Yes, except it's too short. Let's see if I can make it to the terminal. It's still too short or too long. Yeah, okay, now we can see something. So this is the SSHD server, and I don't really know which of these, why there are two processes here, but that is an internal SSHD thing, I think. And here is the special executable I was talking about that acts as a Gitaly client. The only problem is we still can't see the arguments, which is kind of annoying. How shall we cheat? Let me interrupt this and cheat for a moment. Because this is Ruby, it's very easy to cheat. And I can just say here, before we do anything, warn. Oh, it's logging. I don't have to do anything. I just got logged. This thing logged the command we were running. So yeah, what is this command? What are its arguments really? Here's a log file. Okay, great. We have escaping. Let me unescape that. Okay, now it's readable. So it's running this command, gitly upload back. Then it passes the address as the second argument. So that is just the Gitly network address. And then this is a big JSON blob that describes, that gives enough information to establish the session. So that is the storage name default. It has the relative path. Now you can see here that it's still using the old non-hashed format. These things are empty. They have to do with git push. And this is for, this also has to do with git push. And this one is for logging, because in the case that the real path, the real relative path is some hashed hexadecimal blah, blah, blah string, we want to pass along this nice name for logging purposes. So that's why that is in there. Yeah, so that then goes into a Go executable, which establishes an RPC session, which is, I guess, not as exciting. I think it's more interesting to look at, to go into git push a little bit, because git push is more special. And why is git push special? Git push is special because a pool is more or less anonymous. The moment you are downloading data, on the server side, we just generate a pack. Something comes in and says, I want these objects, or I want I see that you have these objects, I have these objects, give me whatever's in between. And then the server just computes that and sends it back. And from the server perspective, this is anonymous. Server doesn't know who is asking for these objects. And we only do an authorization check at the beginning of the session when GitLab-shell makes an API call on the internal API of GitLab. But a push is different because with a push we have two different concerns. One is that every time a push succeeds, we want to trigger events in GitLab itself. For example, trigger CI. So GitLab needs to know that some data was just pushed, and that notification doesn't happen at the start of the Git push session, because at that point it might fail. Also, we don't know what was pushed. You only know that at the end. There are hooks in Git that allow you to where you can get a notification in the form of an executable when a push happens. So that thing needs to report back to GitLab and say, hey, this user pushed stuff to this repo. And when we're in Gitaly, we don't know what the repo is called in GitLab's database. And we also have no idea who the user is, except that we have these keys where these fields where you can say, actually, it was the user with SSH key ID 1. And then on the GitLab side, we translate that back and say, oh, Jacob just pushed something. And the other thing we need when we make that callback from the Gitly server back into the Rails app is to know what is the SQL ID of the project that just got updated. Because we know the directory on disk, but it is not straightforward to do a lookup from that directory on disk to go back to the actual SQL records of the project. In the past, it actually worked like that, but with hash storage, we actually don't have a reverse lookup function, and we're using SHA-256. So if we had a reverse lookup function, we should shop that around with the world's intelligence agencies. So we don't have a reverse lookup, so we need to pass this metadata so that when that callback happens, we can say a push just happened, and the repository, you said that the ID of this repository is this. So this whole back and forth is going on here between this front end and Gitaly and Rails. Maybe I should have prepared this. Does the story make sense so far? Okay, I think it's important to understand this, so let's try desktop. Okay. I hope we have it back now.
Yep, we got it.
Cool. So what happens during git push over SSH? Because that is the most interesting case. So the client connects to GitLab via SSH, the Git client. SSH responds gitlab-shell. GitLab-shell makes API call, well, parses original SSH command and makes API call to /API/v4/internal. That namespace on the Rails application. And then that API responds with Gitaly address repository object. So that means storage name and relative path. Callback information, logical username, logical project name. And those are called, for historical reasons, this one is called GL-ID, and this one is called GL repository, or in lowercase with a hyphen, but the same idea. And what else do we get? I think that is roughly, also important, authentication token. Because the Gitly servers can each have their own authentication token. The GitLab-shell client does not know A, what Gitly servers exist, or B, what the authentication token of each of these servers is. So every time at the beginning of a session, the Rails API responds back with this token. Let me put it up here. So then GitLab-shell puts these things together, uses this metadata to establish SSH receive back session. SSH receive back is the server-side command that corresponds to git push, because from the point of view of the server, it is receiving a pack from the Git client. It's just what it's called. So then we get on the Gitaly side. So Gitaly then spawns git receive back in the right repository directory with environment variables, GLID and GL repository, and maybe a few others. Then git receive back receives git transport data from git client. So from all the way up here, this thing is now pushing data into its, but from the point of view of the Git client, there's just a file descriptor. It's just, it's a socket. So it's just pushing data into that socket. And that then gets encrypted and chopped into pieces and whatever by SSHD and goes across the network. Then it comes out of SSHD and it goes into this GitLab shell executable. And then that GitLab shell executable, GitLab shell reads from standard in, jobs, what should I say, chunks data and forwards across RPC connection. So every time this thing does a write, that becomes a chunk of data that goes through all these layers, and then it reaches standard in of this process on the server, the GitLab server where SSHD is running. Then that thing wraps it in a protobuf message, and then that protobuf message goes across the RPC connection, so the gRPC connection to the Gitly server. Are you still with me? So there's this long chain of that the data has to go through, and Gitly server receives chunk and writes to standard in of git receive back.
Sorry, Jacob. You said that every chunk goes through each lawyer?
Yeah.
I mean, why would we need to, for example, make a request to the internal API?
Oh, yeah, no, thanks. Yeah, no, that does not happen.
That's per session.
Yes.
Right.
So let's say this is per session. So this spawns, let's say this is per session. Data transfer, let's say git session. Let me repeat that. So git client sends git back data, SSH client ships to SSH server. SSH server copies to standard in of GitLab shell. Yeah, okay, I'm breaking down what this means. So that copies to GitLab shell. GitLab shell packages data into gRPC, into protobuf message. Protobuf message goes across gRPC session, or the gRPC connection to Gitaly. So I just did that. And then this Gitly server receives chunk and writes it to standard in of git receive back. So that's the way all that data is going in. At the same time, git receive back prints status out information to standard error and standard out. And that gets, so this is on server. Status information gets proxied back all the way to Git client. And so earlier when, yeah, so if I would now go in Gitaly and, okay, we're running out of time, but I could modify, I could inject some data on the Gitaly server side that would go on the standard error stream and then get echoed back to the client all the way back in the terminal of the client. So this stuff goes back and forth. And after back data is sent, git receive back tries to update refs, and then hooks run. And so this is, again, these hooks are custom GitLab code, and hooks make pre-receive checks, for instance, to block force pushes, for protected branches, and a whole bunch of features. But the ever-growing list of GitLab features is about validating pushes. So that all happens during a hook, and that is an HTTP callback back into GitLab Rails, because all that application logic is defined in the Rails app. So makes HTTP callback request to Rails, and that uses this information. And the reason that information is available is that it is an environment variable on Git receive back. So the hook inherits, these hooks inherit the environment of Git receive back, and that's how we hand down information to the hook, and then the hook can make an API call and say, actually the user has SSH key with ID 1, and it's project with SQL ID 9, and then the GitLab API knows what the hell we're talking about. And so, yeah, and then that finishes on success. Git receive back prints some messages. For instance, it prints messages saying that go here to create a merge request from your push if you push a new branch. That is a message that comes from the GitLab internal API, gets back, sent back an HTTP response to a hook that is a sub-process of Git receive back, and it ends up, so Git then puts it on standard error or standard out. It goes to the Git transport all the way back, and it comes out on the Git client side. But that message originates on the in a Rails process, and exits with 0, and then gitlab-shell exits with 0, and Git client knows push is done. And now it's almost 5 o'clock, so I think we need to wrap up. Yeah. Does anyone dare ask a question?
The hook to call into Rails, what process is doing that? Is that another Gitaly process, or is that a Ruby process?
It is, for historical reasons, it's a Ruby process that lives in the GitLab-shell repository, and we're in the process of copying or moving the code into the Gitaly repository, because it's a process that runs on the Gitaly server. And it's a Ruby process, meaning it's a bit slow.
Got it.
Okay, I should have prepared this a little bit better, because the push is the interesting part, and I should have gotten to that sooner. Maybe we can continue with that next time, or maybe something else.